What's up guys, I'm Seth from Randall Mech. In this video I'll be showing you how I made my 3-axis CNC mill. This included designing, building, and programming everything from scratch. Let's jump right in. First off, a CNC mill is one of two common types of mills. We'll get to the other in a second. In general, a mill uses a spinning tool to cut away material from the workpiece. This tool is held in place with a collet and rotated by a spindle. I used ER20 collets for my machine, which can hold tools up to ½ inch in diameter. The tool and workpiece move relative to each other with certain degrees of freedom. The possible translations and rotations define a mill, so you can have 3-axis mills, 4-axis, all the way up to 12-axis mills, which use two different spindles. I'll focus on 3-axis mills for this video. And we're back! Common mills include manual and CNC. On a manual mill, the axes are moved by hand to a certain extent, using different handles. You can also set the machine to move on its own, but the operator would need to start and stop each motion manually. CNC mills, or computer numeric controlled mills, are run with a pre-written program, typically written with G-codes and M-codes. G-codes control where and how the mill moves, while M-codes control other functions, like coolant and tool changes. These codes can be combined in a single text file for the CNC mill to read. Before starting my project, I wrote out a list of tasks to stay organized. First off, I made a list of my design considerations. I wanted my machine to fit on a table, cut aluminum and possibly steel, have a large work volume, stay quiet for the neighbors even though they're always loud. I wanted to do everything from scratch, keep it cost effective, where it makes sense if you catch my drift, and be accurate to plus or minus a thou. Well, talk is cheap, so let's see if I can follow these specs. Next up, proof of concept. As much as I really wanted a 200-pound paperweight, it wouldn't have made for a very interesting video. So I built the electronics first and tested them. Feel free to pause the video here if you want to take a look at my schematic diagram. I used NEMA 23 stepper motors for motion in the X, Y, and Z directions. I added some crimps and connectors to the ends. I'm driving these stepper motors with, get this, stepper motor drivers. Great name, I know. Which allow me to program every step with an Arduino. I can also incorporate micro-stepping easily. I added a few cables for power, a few more to connect with my motors, a few more to connect with my Arduino, and, well, you get the idea. It's worth noting that each stepper motor driver has wires for pulse, direction, and enabling, which are controlled by an Arduino. To spin my tools, I ordered a 2.2 kilowatt spindle motor. This was massive and weighed over 15 pounds, but it was designed to cut aluminum, it's air-cooled, and holds tools up to ½ inch in diameter. Wait, we talked about that already. Cut to the next part. My spindle motor is a 3-phase motor, so I controlled it with a variable frequency drive. The device converts power from an outlet to 3-phase power. I modified a power cable to power everything, and modified a 36-volt power supply adapter for my stepper motors. And of course, the mill wouldn't be complete without some photo microsensors, a buzzer, an RGB LED, fan to keep the electronics cool, and a tool height sensor. Alright, now that we got those electronics out of the way, why don't we 3D model some stuff? Here's the CAD assembly that I designed in SolidWorks. I'll remove the covers for now to show the different sub-assemblies. First, we'll look at the frame. I designed the frame with a bunch of aluminum extrusions. This was a cost-effective way to add a lot of support. I mounted everything on a base plate made out of ABS, to which I attached rubber feet at the bottom, and a microsensor on top to home the Y-axis. Next up, the work table assembly. My work table has plenty of room for a machinist vise, as well as my tool height sensor. This was super helpful when machining. I designed my fixture plate with an array of 1/4 inch tapped holes so I could add more fixtures in the future. For now, I plugged the holes with set screws to keep them clean. This is a sensor flag that triggers the photo microsensor when homing. I used a ball nut and ball screw, which significantly reduced the backlash on my machine, as opposed to using a lead screw. And here's that stepper motor we talked about earlier, with a coupler which connects it to the ball screw. Next on the list, the spindle assembly. Here we have the most important part of a mill, and my personal favorite, the spindle motor. We also have another sensor in the back, and linear bearings with rails to slide up and down. To move the spindle left and right, I attached everything to a sliding back support. Here we can see another sensor flag, as well as a few more motors. The electronics were comfortably stored in the back, that way I didn't even have to look at them. I sandwiched everything between 2 acrylic panels with mesh around the edges to keep chips out. No short circuits today! I added an itty bitty breadboard to hold a buzzer and a few other wires. I mounted an Arduino Mega 2560, along with a fan, and my amazing stepper motor drivers. And let's not forget my sweet RGB LED. Remember those covers I skipped over? I enclosed everything in plywood and acrylic to keep my apartment quiet and clean. I really don't want to be that neighbor. I also used some foam tape around the edges to seal everything up. Now you might be thinking, what fun is a CNC mill if I can't record anything? Well, I got you covered. With this bad boy, I got all your recording needs satisfied. I mounted a couple latch type toggle clamps to keep the door closed. And that's my design. For scale, here's a yardstick. And a 2020 Chevy Corvette Stingray with red. Okay, enough of that. Let's get to our next phase, building. But first, I'd like to introduce the sponsor of today's video. Yeah, there was none. Now back to building. Throughout my project, I ended up hand tapping about 160 holes. I used a few nuts, bolts, and washers. Okay, a lot. Here's how the wiring came together. It kinda resembles a rat's nest. And to top it all off, I added some dope LED light strips. In the words of the great poet, Lenny Kravitz, it ain't over till it's over, and you finish programming your CNC mill. I'm paraphrasing, of course. Here's an overview of the programs I designed. I used 3 different programming languages. Everything starts with a G-code file, which is read by the software I wrote in the Visual Basic language. The software converts the G-code file and then communicates with my Arduino, which is run off of a firmware I programmed in the Arduino language. The Arduino then sends signals to my stepper motor drivers and other components to control my mill. After opening the software I programmed, I can browse for the G-code file I want to use. I also added a testing mode, as well as some fun little overrides for testing purposes. My software then runs through the G-code to check for any errors, and then shows you where they are. Here are a few that might pop up. I can scroll through my G-code on the left, and I added a robot testing window to test any of my electronics individually. I also have a button to find the length of my tool. I click Cycle Start to home my motors and initiate the program. After that, it's all pina colada until my machine finishes. To prove out my software, I followed the 4 R's of engineering, which are: just get her done. So far, I only use my mill on 3 projects, but I hope to use it a lot more. Here's how they turned out. All that's left is to give this guy a nickname.